When Scientific American heard from chemist Ray Baumann a year ago, he and his international team of nanotechnologists had taken artificial muscle technology to the next level. Their innovation relied on spinning lengths of carbon nanotubes into buff yarns whose twisting and untwisting mimicked natural muscles found in an elephant's trunk or a squid's tentacles. Now the researchers are reporting a new artificial muscle building technique that makes their carbon nanotube yarns several times faster and more powerful. These qualities could help deliver on the technology's promise of developing compact, lightweight actuators for robots, exoskeletons and other mechanical devices, although several challenges remain. The latest breakthrough comes from infusing the carbon nanotube yarns with paraffin wax that expands when heated, enabling the artificial muscles to lift more than 100,000 times their own weight and generate 85 times more mechanical power during contraction than mammalian skeletal muscles of comparable size, according to the researchers, whose latest work is published in the November 16 issue of Science. The previous generation artificial muscles were electrochemical and functioned like a supercapacitor. When a charge was injected into the carbon nanotube yarn, ions from a liquid electrolyte diffused into the yarn, causing it to expand in volume and contract in length, says Baumann, director of the University of Texas at Dallas's Alan G. McDermott Nanotech Institute. Unfortunately, using an electrolyte limited the temperature range in which the muscle could function. At colder temperatures the electrolyte would solidify, slowing down the muscle. If too hot, the electrolyte would degrade. It also needed a container, which added weight to the artificial muscle system. The wax eliminates the need for an electrolyte, making the artificial muscle lighter, stronger and more responsive. When heat or a light pulse is applied to a wax-impregnated yarn about 200 microns in diameter, roughly twice that of the human hair, the wax melts and expands. In about 25 milliseconds this expansion creates pressure, causing the yarn's individual nanotube threads to twist and the yarn's length to contract. Anyway, lifter will tell you that the success of any muscle, artificial or natural, depends in part on the degree of this contraction. Depending on the force exerted, the Baumann team's muscle strands could contract by up to 10%. Muscles are also judged by the weight they can lift relative to their size. Our muscles can lift about 200 times the weight of a similar size natural muscle, Baumann says, adding that the wax-infused artificial muscles can also generate 30 times the maximum power of their electrolyte-powered predecessors. The researchers' latest artificial muscles move the technology closer to commercialized products such as environmental sensors, aerospace materials and even textiles that can't take advantage of nanoscale actuators. University of Cincinnati mechanical engineering professor Mark Schultz wrote in the related Science Perspectives article. This new artificial muscle outperforms existing ones, allowing possible applications such as linear and rotary motors. It also might replace biological muscle tissue if biocompatibility can be established, he adds. However, Schultz points out, and Baumann is quick to acknowledge, that even this new crop of artificial muscles faces many challenges before they can be a practical alternative to mini electric motors in many of the products we buy. Despite their improvements, the latest artificial muscles are for the most part inefficient and limited in the combinations of force, motion and speed they can generate, according to Schultz. Indeed, these new artificial muscles operate at about 1% efficiency, the number Baumann and his colleagues want to increase at least tenfold. An option for improving efficiency is to use a chemical fuel rather than electricity to power the muscles. One way to compensate for a lack of efficiency is to use fuel like methanol instead of a battery, he says. You could store more than 20% more energy in a fuel like methanol than you can in a battery. Another challenge is that the artificial muscles must be heated and cooled to contract and release, respectively. Short lengths of yarn can cool on their own in a matter of seconds, but longer pieces would need to be actively cooled using water or air, otherwise the muscle would not relax. Or you'd need to use a material that doesn't require thermal actuation, Baumann says. If you keep making the carbon nanotube yarn longer and longer, your cooling rate increases. This issue of scale poses perhaps the greatest challenge. The 1 mm length of artificial muscle can lift about 50 grams, according to Baumann. That means lifting several tons would require a greater length of carbon nanotube yarn than is practical. We'd like our artificial muscles to be used in exoskeletons that help workers or soldiers lift objects weighing tons, he says. but the researchers are still working out ways to pack enough yarn to perform such tasks into the length of an exoskeletal limb. Carbon nanotube artificial muscles are more likely to first appear in products requiring only short lengths. Baumann envisions artificial muscles used in a catheter for minimally invasive surgery, where you want to have lots of functionality on the end of the catheter to do surgical manipulations. Another application with FlexAppeal smart fabrics that can automatically react to their environments, becoming more or less porous when they detect heat or harmful chemicals in the air.